This problem is looking at a cooling tower, which has water flowing in through the top of the tower and air flowing in through the bottom of the tower. The water flows through the tower and passes over a series of slats, which serve to make the tower act as a large packed column. The water flows through the slats and comes out the bottom at a lower temperature than it did when it came in through the top. The air will come in from the bottom of the tower, flow over top of the water, which is flowing over the slats. And as it flows up to the top of the water, it will pick up some of the water so that when it comes out of the top of the water, or out of the top of the tower, it will be saturated with water vapor. In this problem, we're asked to derive a series of differential equations in order to solve for the temperature of the air, the temperature of the water, and the mole fraction of the water in the air and water vapor mixture. These equations can be derived using a mass and energy balance for the system. First, we will look at an energy balance for the system using a control volume, which looks at a small slit of the column of height z, so that we're looking at this small change in height of the column dz. The cooling tower is in steady state, meaning that the energy going into the tower is equal to the energy coming out of the tower. In this system, this system is adiabatic and there's no work being done. So when we're talking about the energy in the system, we're talking about the enthalpy of the water in the air. When looking at the enthalpy coming into the system, we have the enthalpy of the water coming in plus the enthalpy of the air coming in, and this will be equal to the enthalpy of the water exiting the tower plus the enthalpy of the air and water vapor mixture exiting the tower. So when we rewrite this equation, we would then have that the change in enthalpy of the water will be equal and opposite to the change in enthalpy of the air. So if we go and rewrite dHW, the change in enthalpy of the water when looking at this small control volume. For a system that's not doing any work, the enthalpy of the system will be equal to the mass flow times the specific heat capacity times the change in temperature. So if we write that here, we have this first section, LW times A, which is the mass flow per area of the water times the area. So this first section in parentheses is representative of the mass flow. Next we have the specific heat, CPW, and the change in temperature, DTW. We can also rewrite the change in enthalpy of the water as the energy transferred during the vaporization of the water that gets converted into water vapor, plus the heat transfer that occurs as a result of convective heat transfer between the air and the water. So that can be written in terms of these two terms. So the first term here is looking at our heat transfer as a result of vaporization of the water. So we have this small a, which refers to the area per volume of the system through which the water can flow, times the area times the length, so times the volume. So this first part of the equation gives the contact area through this control volume. We can then multiply by this specific heat of vaporization, lambda, which would be written in terms of joules per mole, and then we would multiply by the molar flux of the water, so that this would be, or this section right here would be in terms of joules. However, when we're looking at an interface, we can rewrite the molar flux in terms of the mass transfer coefficient times the difference in concentration between the concentration of water at the interface and the bulk concentration of the water. So this first term is looking at heat transfer due to vaporization of the water. The second term, when looking at enthalpy of the enthalpy of the water, we have the convective heat transfer that is occurring between the water and the air. So here we have our convection heat transfer coefficient times the difference in temperature between our air and our water. So this equation gives us the change in enthalpy of the water in this control volume. So we can also write the change in enthalpy of the air for this control volume. So this can be written in the same way. So first we have the mass flow of the air and water vapor mixture per area times the area times the specific heat of air times the change in temperature of air. Oh, I forgot to mention in the DHW equation, this first term, the heat of vaporization, will be negative. And this is because Z is increasing as we go down the column rather than going up the column. So in order to account for the fact that as Z is going in the positive direction, the temperature of water will be going in the negative direction because the water will be cooled as it goes through the column. We have to put this negative sign out front. But okay, yes, so enthalpy of air can be written as mass flow of the air per area times the area times the specific heat of air times the change in temperature of the air. And this can also be written in terms of the heat transfer resulting from the vaporization of water and the convective heat transfer. So once again, we have this contact area, this first section of the equation, times lambda heated vaporization times the mass transfer coefficient times the difference in concentration of air between the interface and the bulk flow. So we have the contact area times specific heat of vaporization times the molar flux of the air. And that is for heat transfer from from vaporization of water. And then the second term is the heat transfer resulting from convective heat transfer between the air and the water, I think. So once we have our energy balance equations, so once we have our equations for the energy balances of the system, now look at the mass balance. And so, and just as how in our energy balance, we had the energy that was being transferred between the air and the water. So like the energy that was being absorbed by the water when it was vaporizing, and the energy that was being transferred from the water to the air, the energy that was, and the energy that is being convectively transferred between the water and the air would lead to the change in enthalpy of the water being equal to the change in enthalpy of the air. In a similar fashion, when looking at the mass balance, the change in mass flow of the water, so the change between the flow of the water at the top of the column and the bottom, that change in mass flow can be accounted for the mass of water that is being picked up by the air, or well, is being vaporized and picked up in this airflow, and exiting the top of the tower as water vapor. So this amount of mass flow that's being lost by the water as a result of vaporization will be equal to the mass that is being gained by the airstream because it's gaining that mass of water vapor. So when looking at the change in mass flow of the water in our control volume, we have the mass flow of the water per area times the area. And we can rewrite this mass flow per area of water in terms of the total mass flow per area, this G, which is the sum of the mass flows of the water. So the mass flux per area of the water will be equal to the total mass flux times the mole fraction of the water. But then because we're looking at mass flux rather than molar flux, to account for the difference in molar mass between the air and the water, we then need to multiply by the ratio of the molecular weight of water compared to the average molecular weight of the mixture. And this average molecular weight can be found by this equation here, where we have the sum of the mass flows of the air and water divided by the mass flow of the water over the molecular weight of water plus the mass flow of the air over the molecular weight of the air. So once we have this value, we can then rewrite our flux of water in terms of its molar flux. So here we have the mass flow of the mixture per area times the area. But since we're now writing it in terms of molar flux, we'll divide by the molar flux, the molar mass of the mixture, so that this value of mass flow will now be written in terms of molar flow. And then to get just the molar flux of the water, we then multiply by the mole fraction of the water, so dy, in the vapor. And then finally, we can set this equal to the molar flux of the water, written in terms of our mass transfer coefficient times the difference in concentrations of water at the interface and in the bulk flow, and multiply once again by this area of contact that is occurring in the control volume. So we now have these three differential equations for looking at dTW, dTA, and dy. However, these can't be used yet because they all include this mass transfer coefficient, Kc. And Kc depends on the film thickness at the interface between the air and the water. And this was not given to us in the problem because it's difficult to measure. So instead of determining Kc from a given value of the film thickness, we need to solve for Kc using the dimensionless numbers that we were given in the problem. So this includes the Nusselt number, the Sherwood number, the Reynolds number, the Schmidt number, the Prandtl number, and the Lewis number. So it's given in the problem that the Nusselt number for this system is equal to 0.6 times the Reynolds number to the 1/2 power times the Prandtl number to the 1/3 power. And we know that the Nusselt number is the ratio of convective heat transfer over conductive heat transfer. We also know that the Sherwood number is the ratio between convective mass transfer and diffusion. So the Sherwood number and the Nusselt number are related because they're both looking at the relationship between convective and conductive transfer. The Nusselt number is looking at transfer of heat, and the Sherwood number is looking at the transfer of mass. So because the Nusselt number and the Sherwood number are looking at the same type of ratio, we can rewrite the Sherwood number using the same relationship that we have with the Nusselt number. So this 0.6 times the Reynolds number. The only thing that we have to change is that while in the Nusselt number we're using this Prandtl number to the 1/3, where the Prandtl number is the ratio between the momentum diffusivity and the thermal diffusivity, with the Sherwood number, because we're looking at mass transfer rather than heat transfer, we want to look at the relationship between momentum diffusivity and molar diffusivity. So in this case, we'll use the Schmidt number. So if you put the Sherwood number and the Nusselt number into a ratio, this 0.6 times the Reynolds number to the 1/2, these terms in both of the equations will cancel out. And so if we have the Sherwood number over the Nusselt number, this will end up simplifying to the Schmidt number over the Prandtl number to the 1/3 power. And we know that the Lewis number, which is the ratio between the thermal diffusivity and the molar diffusivity, is the ratio between the Schmidt number and the Prandtl number. So if in this problem the Sherwood number divided by the Nusselt number is equal to the Schmidt number divided by the Prandtl number to the 1/3 power, this means that this ratio is also equal to the Lewis number to the 1/3 power. But we can also rewrite this ratio between the Sherwood number and the Nusselt number using the individual components of the Nusselt number and the Sherwood number. So for the Nusselt number, this means the convective heat transfer coefficient times the dimension divided by the thermal conductivity. And for the Sherwood number, we have the mass transfer coefficient times the dimension divided by the molar diffusivity constant. So when we plug these individual values in for the Sherwood number and the Nusselt number, we end up getting the mass transfer coefficient times the thermal conductivity divided by the molar diffusivity times the convective heat transfer coefficient. This term right here, we can then rewrite in terms of the Lewis number. We know that the Lewis number is the Schmidt number divided by the Prandtl number, which we can then rewrite in terms of the thermal diffusivity over the molar diffusivity. And this thermal diffusivity can be farther broken down as being the thermal conductivity divided by the density times the specific heat capacity for a substance. So we can rewrite the Lewis number as being the thermal conductivity divided by the density times the specific heat capacity times the molar diffusivity. So if we want to then rewrite this term over here that represents the ratio of the Sherwood number to the Nusselt number in terms of the Lewis number, we can then put in this K over P Cp dAB into this term. So all we have to do that is multiply and divide by 1, so we're multiplying and dividing by the density and the specific heat capacity to get this term in our equation. So then we'll end up with the ratio between the Sherwood number and the Nusselt number being equal to the mass transfer coefficient times the density times the specific heat capacity divided by the convective heat transfer coefficient times the Lewis number. So then we can take this Lewis number to the 1/3, and this term we have here, this KCP or KPCP divided by H times the Lewis number, and set these equal to each other in order to solve for Kc. So when we set these equal to each other, that we can put the Lewis numbers all on the same side of the equation. So then we'll get Kc times P times Cp divided by H is equal to the Lewis number to the -2/3 power. And it was given in the problem that the Lewis number is approximately equal to 1. 1 to the negative 2/3 is equal to 1. So therefore, when we solve this equation for Kc, we'll get that the mass transfer coefficient is equal to the convective heat transfer coefficient divided by the density divided by the specific heat capacity. So we can now plug this value for Kc into our differential equations. So once we plug our formula in for Kc to each of our, so once we plug in our formula for Kc, we'll then be left with 3 differential equations which we can solve to find the temperature of the water, the temperature of the air, and the mole fraction of the water in the vapor. So here we have our formula for dTw, which will solve for Tw, our formula for dTA, which will solve to get TA, and our formula for dy, which will solve to get the mole fraction of water. One last thing, I think I made a mistake on this energy balance for dHW. For this negative value, which I explained was accounting for the fact that D is increasing as you go down the column, I'm missing a parentheses here. This negative should encompass this whole equation, not just this first term. So it should be negative for this whole thing. And then over here, it should also be negative for this whole thing.